Question 4 is about mean bond enthalpies. So I've got the bond enthalpies of each of the bonds in these reactants and products. So what I've got to do is I've got to calculate the strength of the bonds on the left hand side and calculate the strength of the bonds on the right hand side. These bonds here have been broken, so these are my reactants and those bonds get broken, and in the products, the things that are made, bonds are formed, and you take this value, the value of all of the bonds broken, and you take away the value of the bonds being made, and that'll equal your enthalpy change. So it's the strength of all these bonds, take away the strength of these bonds on the right hand side equals minus 49. So what I've actually got in there, so let's do spoilers. I've got CO2, I've got 2 lots of CO, I've got 3 lots of H2H, and I haven't got that value, that's what I'm trying to find out. So my bonds broken are 2 lots of 743 plus 3 lots of HH, I don't know that, and the bonds formed, and here I've got CH3, so I've got 3 C2H's, so I've got 3 412s. I've got a carbon to oxygen, so I've got a 360, and I've got an O to an H, so I've got a 463, and in H2O I've got HOH, so I've got 2 OH's, so I've got 2 463. So minus 49 is 2 times 743, add the 3 H to H bonds that I don't know, take away, so I'm taking away, subtracting the values of the bonds that are formed, so bonds broken take away bonds formed, so I've got 3 times 412 are my CH's, C2H's, I've got a carbon to oxygen, which is a 360, and then I've got an O to an H, and I've got 2 more O to H's here. I've got 3 times 463, and if I resolve all that, minus 49 is 1486, add 3 lots of the H2H bonds, which I don't know, take away 285, take the minus 2985, take the minus 2985 across the other side, it becomes a plus, 1486 plus becomes a minus, and that equals 1450 is the value of 3 H2H bonds. So 1 H2H bond is 1450 divided by 3, 483. Suggests one reason why a data book value for the HH bond is different from that, because these are real values, they're not mean bond enthalpy values. So the true values are not actually mean bond enthalpy values. So the mean bond enthalpy values are not the same as the actual or true values of the enthalpies of the actual chemicals. The bond enthalpies in a real reaction actually change from the average bond enthalpy. This is just an average bond enthalpy over a number of different reactions. It's just one environmental advantage of manufacturing methanol fueled by this reaction, using up carbon dioxide. Use Le Chatelier's principle to justify whether the reaction is carried out at high pressure rather than atmospheric pressure. Let's have a look. So I've got 1 mole of carbon dioxide and 3 moles of hydrogen. I've got 4 moles of gas on the left hand side. I've got 1 methanol gas and 1 water gas. I've only got 2 moles of gas on the right hand side. So I've got 4 moles of gas on the left, 2 moles of gas on the right hand side. So if I increase the pressure by Le Chatelier's principle, increasing pressure, Le Chatelier's principle will try and lower the pressure. It lowers the pressure by turning a large volume down in a small volume. It'll shift the position of equilibrium to the right hand side to lower this pressure by Le Chatelier's principle and increase the yield of methanol in the process. Suggests why a catalyst used in the process may become less efficient if carbon dioxide contains impurities. Well, a catalyst has got active sites just like an enzyme. So it locks in the molecules and brings them close together. So impurities will block these active sites. In a laboratory experiment to investigate, we've got an equilibrium reaction here, and we've got some values of some of the chemicals before the reaction started. Then at equilibrium, we will need to work out the values of each of them at equilibrium and work out an equilibrium constant. There's Kp here, which means it's they're all gases, so it's not got concentration, it's actually the pressure of each of these. If you've got gases, then pressure is the same as concentration, so you can place concentration with pressure if you've got all gases in a reaction. So let's do spoilers first of all, so you can see how I'm going to set this out. So carbon dioxide and 3 moles of hydrogen, making 1 mole of methanol gas and 1 mole of steam or water. initial number of moles, 1 mole of carbon dioxide, 3 moles of hydrogen. It doesn't mention anything about the methanol and the water, so we haven't got any of those. And at equilibrium, it says at equilibrium the yield of methanol was 0.86, so I've got this value here. Now when 1 mole of methanol's made, 1 mole of water's made, 1 and 1. So one of these and one of these are made at the same time, so this must be 0.86 as well. So they're made in equal amounts. 1 mole of carbon dioxide makes 1 mole of methanol, so if I'm making 0.86 moles of methanol, then 0.86 moles of this must be used up because it's a reactant. 1 mole of carbon dioxide reacts with 3 moles of hydrogen, so 3 times 0.86 or 2.58 must be used up. Let's have a look what I've got in the equilibrium mixture. I started with 1, I've used up 0.86, I've got 0.14 left. I start off with 3 moles of hydrogen, I've used up 2.58, 3 take away 2.58 is 0.42, and I've got 0.86 of this made and 0.86 moles of water made as well. So what I actually do is, for pressures, for concentrations, then I take the amount and I divide by the volume. So the total volume is 2.28. When I add up all of the volumes of each of these, or numbers of moles of each of these, that equates to volume as well. So number of moles can equate to the volume. So total moles of gas, 0.14, 0.42, 0.86, 0.86, 2.28 moles of gas. And what I therefore do is I work out the fraction of carbon dioxide that I've got. So I've got 0.14 moles of carbon dioxide. So I divide therefore, so the fraction of carbon dioxide in the mixture, I've got 0.14 moles out of a total of 2.28 moles, 0.061. So I work out the fraction of carbon dioxide in the mixture. Hydrogen 0.42 divided by the total number of moles 2.28 is 0.184, so that's the fraction of hydrogen that I've got in the mixture, and I work out the fraction of methanol and the fraction of water as well, 0.377. So now I've got the fractions of each of these contributing to the total pressure. So 500 kilopascals is the total pressure, and the fraction of carbon dioxide that I've got in the mixture is 0.061. So I'll multiply the fraction by 500 and I find out the pressures that each of these are contributing. So the number of moles, or the fraction of the number of moles, then gives a fraction of the pressure. So these are the pressures that I've now got. So I multiply the fraction of number of moles by the total pressure, and I work out the fraction of the pressure that's been provided by each of these. These last two are calculated by multiplying 0.377 by 500 to give 188.6. And if you add up all of those, it should equal 500. Now, an equilibrium constant is would be the concentration of methanol multiplied by the concentration of water divided by the concentration of carbon dioxide divided by the concentration of hydrogen to the power 3. It's the same for pressures, so I'm just replacing concentration with pressures, and I put these values in now. Each of these pressures, called partial pressures, I put those in and work out a value is 0.00151. So that's my equilibrium constant, or my Kp, 0.0051. And then I do the same things again. I've got pressure times pressure divided by pressure times pressure to the power of 3. So I've got kilopascal twice on the top, and kilopascal multiplied by kilopascal, kilopascal per kilopascal. So I've got 4 kilopascals on the bottom. So 2 kilopascals cancel. I end up with 2 kilopascals on the bottom. And that's kilopascal to the -2 if I take it to the top.